This video looks at the mechanistic lead compensation design technique using MATLAB tools. So the previous video showed what the links were between the key attributes of a lead compensator and margins, and from these links we proposed what could be called a mechanistic design approach, something that's basically explicit so students can try it and get a reasonable answer. Now this video is going to show how you can use MATLAB tools to do this design very efficiently and quickly. Just a reminder then of what these rules are. First, you have to choose the desired gain crossover frequency omega, and you're reminded that this should be higher than the gain crossover frequency you can get with a simple gain design, otherwise you're wasting your time. Then what you need to do is specify a desired phase margin and solve this particular formula here. The argument of g of j omega plus a equals phase margin minus 180, and solve for a. But remember that in your proposed phase margin you must ensure that the a you end up with is less than 55. Right, once you've found the required phase rotation a, you use the lookup table to find the required beta value for your lead. So here's the table here. So you'll see that the phase rotations are given in this row and the corresponding beta in the top row. And I would recommend you just do it to the nearest integer because the differences are small otherwise. Then what you need to do is choose the gain of the lead so that omega is indeed the gain crossover frequency, and we gave you an explicit formula to make sure that happens, and this is the formula here. So what you'll notice is you take the gain crossover frequency omega, that goes in there, you take your beta, that goes in there and in many places, and you'll notice the other thing, oops, that wasn't supposed to happen, the other thing in the formula, oops, something's gone wrong there, is the modulus of g of j omega here at the bottom. The key thing is this formula is explicit. Okay, so if you make your choices, and your choices are the gain crossover frequency and the phase margin, then the formula will drop out. Okay, so what we're going to do, we're going to use OToole to demonstrate this procedure. We're going to use 3 examples, and you notice the first example, this one here and this one here, are the same as we used in video 10, and we've done that deliberately so that you can compare the lead compensator we get with this mechanistic design to the lag compensator from the mechanistic design and see what the differences are between the two. Where possible, we're going to use a desired phase margin of 60 degrees because that's consistent with what we did with a lag. But do remember that to some extent that is arbitrary. So we're going to start now with this G here as example 1. So we need to first go to OToole. So that's what we're doing here. We're just opening up the relevant OToole windows. So here's example 1, and we've put in the simple gain design which was done in video 10. So you can go and look at video 10 if you want to see what was going on. And the key thing to note down here is you'll see that the crossover frequency was 0.164. Now what we've said is for the lead we should be able to increase this. So how much do you want to increase it? Well, remember we can only increase it until the phase margin here is basically the smallest we can let that phase margin become is 5 degrees, because then when we added a phase rotation of 55 it would get back to 60. So what I'm going to do is basically increase the crossover frequency by pulling up the gain plot. You'll see as the gain plot goes up, but you'll see the phase margins going down and down and down. So if I stop somewhere like that, this is relatively arbitrary, you'll see the phase margin is now 14.7 degrees and the crossover frequency is now 0.275. So you'll see it's nearly double what it was before. Now, with a phase margin of 14.7 degrees, we're going to need a rotation of about 45 degrees. And if you look back at your table and say, okay, what did we need to get 45 degrees? The beta we required was about 6. So what we should do, in fact, if I'll go back here and let's look at the formula. So this was the formula we had. Oops, I didn't mean to do that. What I meant to do was just rub this bit out so it's not in our way. So there's our formula, and what we need to remember is, what did we have? We had omega equals 0.275 and beta equals root 6. So that's the formula we're looking at. Now, how are we going to get that into the system? Now, we could put it direct into OToole, but in this particular case it will probably be easier to enter this directly into the MATLAB window. So that's what I'm going to do here. So I'm going to write K1 lead equals TF. Now I'm going to need a lot more space, so let's make this a bit bigger. Okay, so first of all, we wanted to know what the 0 was. Well, the 0 was 1, comma, now omega was 0.275, so let's put that in 0.275, and it was divided by root beta, so that was the square root of 6. So that was the numerator. And then the denominator was 1, comma, 0.275 times the square root of 6. So you see, I can put this formula direct into MATLAB and without actually needing to do the calculation separately, so it's much neater. So that's the first part of the K-lead. Now, the next bit is, of course, I didn't add the gain multiplier, and that was deliberate because of space. So out the front we have the square root of 6, and then we divided by the gain of the system at this frequency. Well, I can get the gain of the system using Bode G1, 0.275. So that should give me the gain of the system at a frequency of 0.275. So if I do that, and if we just make this window a bit bigger so you can see the result, there is your lead compensator. So assuming I've not made any silly mistakes, I should now be able to absorb that into OToole. So let's go here, and let's import compensator, and what we want is K1 lead. So let's go OK. Now if we did it correctly, you'll see, lo and behold, what have we got? A phase margin of about 60 degrees, a crossover frequency 0.275 as expected. So what that's telling you is that we've done it pretty much correctly. And here are the responses. You've got the input and output responses. It does look a little bit oscillatory, which is somewhat surprising. But what we'll do next is we're going to go to our command tool here, and let's first of all overlay all the Bode diagrams for all these different systems. So we've got in here, you'll notice we've got the lead, we've got the lag, we've got the simple gain. Let's just put the fonts up there so you can see which is which. So the uncompensated in dark blue, the simple gain design in green, the lag in red, and this sort of lightish blue is the lead. And you can see the difference in the Bode diagram. So what's the lead done? You'll notice the lead has got a higher gain, a high frequency, as expected, whereas the lag has got a higher gain at low frequency, as expected. So the lead is giving you a high bandwidth, high speed of response, but not dealing with the steady state very well, whereas the lag is not too worried about bandwidth and speed of response, but it deals with the steady state. You look at the phase diagram down here, you'll see the lead has got a lifted phase diagram around the crossover frequencies, and the lag has got this phase dip at low frequencies. What about responses then? So if we overlay all the responses, and what do you see? They all seem quite oscillatory for this system, but I think it had some, some complex roots in it, so that's probably why. So if we have a look, first of all, at the step responses, what do you notice? Simple gain design is the blue. That's got quite a sizable offset. The lag is the green, and that's got the smallest offset. And the lead, although it's got the fastest response, you'll see the lead actually has the biggest offset. Now if you want to see the speed of response comparison, let me just go and put an xlim in here. Let's see if that will no, it wasn't that one, sorry, I've done the wrong figure, that one. No, dear. Oh, here it is. There you go. Now, so this is the transient behavior, and what you see is you see the lead has got a much faster rise time than the lag and the simple gain design. So that's what you're getting from the lead, a much faster rise time, but it did have a bigger offset. Now if you look at the price we paid for that, look over here at the input responses, and you'll see the lag and the simple gain design, the input starts around 10, whereas with the lead, the input starts around 40. So you've got a much more aggressive actuation, and that's the price you've paid to get this much faster response. So you only really want the lead if you need this faster response. Okay, let's move then to example 2. So there's example 2. And we'll just make sure we've entered all of the compensators. So what I've got to do now is go to OToole and import example 2. So first of all, clear all our designs, and then import G2. Okay, and just remind myself, so 0.065 was the design we got in the previous. I thought we cleared the compensators. Something's not gone right here. Let's just try that again. And design, clear all compensators. There we go. So now let's put in 0.065, which was our simple gain design, and yes, we've got about 60 degrees. So that's what we did in video 10. So what are we going to do with the lead? Same as before. What we're saying is we want to increase this gain crossover frequency. It's currently at 1.13. So let's drag up this gain plot and see how much bandwidth can we actually get. So I'm going to go quite far this time. I'm going to be quite aggressive. So what do you reckon? Somewhere around... Sorry. There we go. Somewhere like that. Now you'll notice here the phase margin's gone down to 12 degrees. And the crossover frequency's gone up to 9. I've increased the bandwidth by a factor of about 9, which is huge. Okay, and because I now need a phase rotation of about 48 degrees, that's going to be a beta of around 8. So what you need to remember is this number, 9.43, and a beta of about 8. So let's go and go back to the MATLAB command window, and let's enter this compensator. So I can go back to the command I used before and just change the numbers, then we'll see the structure. So it's K2 lead, and so with the frequency we now said was 9.75. Okay, so let's put that in both places. 9.75. We said the beta we were going to use would be 8, so let's put the 8 in there. So that's the first part, and then we had K2 lead equals K2 lead times, and it's going to be the square root of 8 divided by Bode G2, 9.75. Okay, so there's our lead compensator, just using that explicit formula. So now I can import this. So import, and we'll put it there, K2 lead. Okay, and you'll notice, as expected, the phase margin about 60 degrees, now it's 62.6. Okay, and the crossover frequency where we expected, 9.75. So you'll notice this explicit design is delivering what we want it to deliver. Now, let's just look at the Bode diagrams, before and after, as before. So let's just find out where those Bode diagrams have gone. There they are. And what do you notice? Exactly as before, you'll see that the lead has got this significant lift in the phase plot. Here you see it down in the bottom right. And the lag has got this classic phase dip. But with this one we really did get a huge increase in bandwidth, and that's why you can see this significant difference in these two plots over here. What about the gain plots? Well, where's the lead? I'm struggling to see it. It's probably this one here. over here. See this top one? So a very high gain at high frequency from the lead, and still a reasonable gain at low frequency because we had such a high gain over here. Whereas the lag was a much more cautious policy. Alright, let's do the step responses and see what they tell us. Okay, so here's the output step responses, and what do you notice? The responses are all very smooth. You can see we had the simple gain in blue, we had the lag in green, and we've got the lead response in red, and you see the difference between the red, the green and the blue is just the speed. It's much faster. So again, if I do this xlim command to limit my x-axis so I can see a bit more of what's going on. Oh, sorry, I keep going to the wrong window. There it is. And again, you can see here, it really is much faster than you've got from the other two compensators. And in fact, you wouldn't be surprised if it was about 9 times faster, because you increased the crossover frequency by a factor of about 9. But what price have you paid to get this really fast response? Well, let's look at the input signals. And what you notice, there are the input signals for the simple gain and the lag compensator, those tiny ones down at the bottom that you can hardly see, the green and the blue. What's the lead input signal? It's this red one. It's very aggressive indeed. So nothing is for free. You've got this very fast response, but you've paid for it by having very heavy actuation. And so you have to decide, what do I want? Do I want speed of response and a powerful actuator, perhaps very aggressive control, or do I want nice smooth behavior but more cautious control? And therefore you can choose between a lead and a lag. Alright, let's go to the last example now. And the last example was slightly more challenging because it was an unstable system. So let's enter it. It's G3, and let's go to our OToole window. There it is. So first of all, let's clear all compensators, and now let's import G3 and see what we can do. Now you remember, with open loop unstable systems, we have to have something's gone wrong here. Let me just check. Has it actually cleared the compensator? No, it still hasn't cleared the compensator, so let's clear that again. Right, now it's cleared. Okay, now with these open loop unstable systems, you often will need a lead compensator design to stabilize the system in the first place. So first of all, we've got to decide what is a reasonable gain crossover frequency and phase margin to achieve. And this is where OToole is so powerful, because if you look at this window here, you can see the current phase margin. It's this brown line here. And you know that a positive phase margin means this brown line has to be above minus 180 degrees, whereas currently it's below. But you know that the phase lead can lift you by up to 55 degrees. Now at the moment we've got a phase margin of minus 59, so if I lift that by 55, it's still going to be negative. So I can't choose this gain crossover frequency because I can't get enough lift from the lead. So I've got to move this brown line over here to the right before I can actually create a positive phase margin with the lead. So what I'm going to have to do is, in order to increase this gain crossover frequency, I've got to move the gain plot up. So that's what I'm going to do. You see, as I drag the gain plot up, you can see where the phase margin line moves and moves and moves. Now how far do you want to move it? You can choose, but let's say we move it there. So the phase margin is now minus 15 degrees. Okay, now at minus 15 degrees, if I use a phase lift of 55, I can turn that phase margin to plus 40 degrees, which might be reasonable for an unstable system. So that's why I've stopped roughly there. I've stopped at minus 15 because, of course, to make the phase margin even smaller, I need more gain, and there's a limit to how much gain I can get. So let's look at the numbers we've got. We've got a frequency, I'll call it 7.2 for simplicity. I've said I want a phase lift of 55, which gives me a beta of 10. So remember those two numbers, 7.2 and a beta of 10. And let's go to our MATLAB window and let's enter our compensator. So we'll have K, oops, that'll do. We'll just change one of the early ones, so K3 lead, Oops, sorry, I've got the wrong one there. That was careless. That's the one I want, so let's do that. So we had the square root of 10, and we had a frequency of 7.2. So you'll notice I'm simply plugging in my explicit formula and using the command window to enter it, because it's a bit quicker and easier than putting it directly into OToole. So there's the dynamic bit, and then the gain part was we want the square root of 10, and then we have to divide by the gain of the system at the specified frequency. Oops, it was G3, not G. There we go. So there's your lead compensator. So let's import that and see whether it's worked. So we go import, and we'll put in here K3 lead. Go OK. Has it worked? And what do you notice? Our phase margin is about 40 degrees, which is what we expected. Our crossover frequency is 7.2, which is what we expected. And you can see also that the phase margin is pretty close to this phase peak, which is also what we wanted. Now you might want to ask, have I got reasonable responses? Well, there's the input and output responses, and you can see, yes, the input is very aggressive indeed. It's gone all the way up to 50, but the output looks quite nice, as we expected. If we want to get the scales, it might be easier to look at this in the main MATLAB window. So perhaps if we do that, let's go here and go down. Oh, we've not actually put the command in, so perhaps if I write it directly. So we go overlay many, and you want G3 and K3 lead. And you'll notice I've only done one plot because it's not stable with simple gain design. So that's what you've got. And yes, there is quite a sizable overshoot on this output, but you might argue that because this system is open loop unstable, it's going to be quite difficult to get nice behavior out of it. You might be happy enough to stabilize. Okay. So in summary, we've shown a number of worked examples using MATLAB tools to perform a mechanistic lead design. Now, we've reinforced the observation on lead compensators that they improve margins by rotation and hence allow high bandwidth relative to lag designs. However, what's the price of this? Control can be aggressive, and you may get a poor low frequency gain. If you remember with example 1, we had a much bigger offset in steady state, so faster rise time, but then a bigger offset. A lead is essential for open loop unstable processes where a lag is not appropriate. And a lead is a high bandwidth option, and thus it may not be suitable where you want cautious control or robust behavior is required.